How's it going? So, end of day one. Hope you guys have enjoyed the presentations throughout the day. So today I'm going to talk about Apache Ignite using a memory grid for heterogeneous on the agenda. It's distributed. Not too sure why that word changed, but it's going to be distributed and heterogeneous. It's going to be an awesome two-for-one deal. And then computation framework. And the way that I'm going to go through this is with a use case guided exploration. So what we're going to talk about is who contributed to this presentation, the use case, what we're going to talk about. I'm going to give you a little bit of background on that. The requirements that we had and the several approaches, in this case the 3 approaches that we had taken in order to achieve those requirements. The lessons that we learned, and then kind of what are we doing with this next. So first of all, I'm Chris Herrera. I'm from Hashmap. We are a big data, IoT, a lot of buzzwords, consulting company. We're based in Atlanta. I'm actually from Houston. Mostly what I do is oil and gas, and you're going to see an oil and gas related topic today that we're going to explore what we've done with Ignite with the distributed and heterogeneous compute. So I wanted to quickly mention the 2 other team members who contributed greatly to this project, Jay and Akshay, who are from our office in Pune, and then myself. So I am the Chief Innovation Officer at Hashmap. What that means is I lead an accelerator division, and that's pre-engineered software assets that we use in order to kind of accelerate our consulting engagement. So let's quickly spend a little bit of time talking about the use case and why we ended up using Apache Ignite to handle some of our distributed compute and our heterogeneous compute needs. So quickly, I'm going to teach you how to drill a well. That's what we're going to do right now. So here's the process. You've got a very happy reservoir engineer. He's going to make a plan. You're going to actually drill the wells. There's going to be some data that goes to a WITSML server. It's going to do some amazing magic, and then you're going to make a whole lot of money. This is what most people actually want to do in drilling. Absolutely nobody's actually doing this right now. It's very, very difficult. Let's take a look at why. So if we take a look at what the plan actually looks like, when you're actually planning, you've got a bunch of different engineers who are working on planning the well, getting the financing for the well, understanding how long the well is going to take, what type of measurements do they need to get while they're drilling the well, what type of equipment do they need while they're actually drilling the well. Separately, you've got a whole other group of people who are worried about who are the vendors who are going to drill this well. To drill a well takes about 85 people on a rig. How are we going to pay for it? And then there's a whole bunch of homegrown databases that are thrown into this. And this is just the planning side. Makes for a very sad data analyst. So what you end up with is kind of the standard stuff that you have, which is how you're going to match the data, how do you deduplicate this data, what's the missing information, how do you find the missing information, the various formats, and the various ingest paths that you have from it. Now, when you're actually drilling the well, there's a bunch of people who collect data and stream that data in. So we've got a measurements while drilling engineer. They're responsible for putting the tools in the hole, collecting the data from down in the earth, sending it back up, and sending it off. The mud logger who actually looks at the geology, the rocks. The cementer who's responsible for cementing the steel tube in place that goes in after you've drilled the well. And the wireline guy who goes in and makes sure you did all that right. Now, this data comes in via WITSML, which is an Oilfield standard. It stands for Well Site Information Transfer Specification Markup Language. It is pretty brutal. It is a SOAP RPC specification that just transmits gigantic XML documents, essentially. They're CSV files shoved into an XML document. Then you've got CSV files that are generated by the cementer. How those CSV files are actually generated is up to the cementer. It's kind of special. And then DLIS, which was a digital variation of a format that was originally intended for tape drives. Now, this is actually sent via WITSML server, and then honestly, this goes through via some sort of magic. Normally, what that means is that some guy in a truck might or might not deliver the data. It's really dependent up to the guy in the truck. Again, we have a sad data analyst. You've got the situation of missing classification, unknown quality, various formats, various ingest paths, and unknown completeness for your data sets. So when you're looking at the entirety of oilfield drilling data processing, you've essentially got the entirety of your well planning information and your master data. All of your real-time data, the top two are coming in real-time or near real-time, and the bottom two are coming in, depends, real-time or not at all, or sometimes on a truck. And this all leads to a very angry data analyst. Now the problem is, you're trying to match all of this messed up data, parse it, enrich it, and combine it in real time. So that's the problem that we're facing, and we've actually faced that with a number of different oil field clients. In this scenario, you end up with a situation where you've got, it's almost impossible to generate insights, and if you do, you had a huge data cleansing operation. So to give you some actual metrics on this, about 2% of all this real-time data that's ever generated is actually used after the operation is over. Only 2%. That's worldwide. From the CSV and DLIST files, it's closer to 10%. But actually what happens is once the operation is over, this data is forgotten about. And they actually only take a subset of what's called recorded mode data. And the problem with that is in the drilling world, there's a big emphasis on operational improvement and efficiency, which you only get through the time series data, which is never captured again. So it is extremely important that we start collecting this data, enriching it, making it usable while we're actually collecting it. So the bigger problem with this is what actually happens at the back end. What are you actually going to have to do to this data to make it usable? So we have to start with parsing the data. And again, the WITSML, DLIST, it's full, like a lot of industries, it's full of very specific specifications that are specific to that industry. You have to identify and enrich that data. When you are looking at enriching this data, this is making sure that you've got the correct well name, the surface location is correct, you've got the right vendors who are actually on that well, that you even know it's kind of odd, but a lot of times they don't even know what the well was called when it was drilled because some guy with gloves that are about this big tried to type it in. Loading the data into a staging area to start understanding what to do with it, cleaning it, which is that dedupe, interpolation, pivoting of the data, aggregating it, and then splitting it to create training sets and training sets and test sets. And then feature engineering. So in feature engineering, there's a lot of additional information that you have to infer out of the data. So what I mean by that is while you're drilling, you only have kind of these discrete sensor points that you're reading from. From that, you have to determine whether or not the bit is actually on the bottom of the hole. You have to determine what the rig crew was doing just based on sensor. And you don't have video, you don't have audio, you don't have anything else. You've just got that time series sensor data to work off of. So there's an inference engine that comes into this. And then there's persisting and reporting. Now, a lot of this doesn't sound like a lot, but when you get down to the feature engineering and the persisting and the reporting, a lot of times you're actually doing a lot of joins and a lot of combinations on data sets that are anywhere from, on a large multilateral well, you could have upwards of 6 to 7 billion time series points from a multilateral well. You start combining that in a spatial area, and you're in the very high billions, tens of billions range to be able to actually start identifying patterns, doing things like shapelet analysis, shapelet detection to excuse me, to determine potential failures, things of that nature. So there's actually quite a lot that goes into this. A lot of this code actually exists today. The problem is reusing that code. Because what ends up happening is when we go into an office, a lot of times the client, the operator that we're working for, does not want to invest the time and the energy into porting that code over to something else. It could be Java code, It could be C++ code. It could be something written in Spark, Flink. It depends what it is. So let's quickly go through and see, based off of what we talked about, what we kind of have to bring out. And we're just going to see the architecture that we built to handle this and see how we used Ignite to do that. So first of all, we had to parse the WITSML and the DLIS. CSV and the CSV files were not a big issue. Attribute mapping, which is to say there are situations where you'll have time, and time will be TIME, and there are situations where you're going to have time, and it will be called Bob. It'll be called whatever they want to call it. Unit conversions. There, we have had depths. So wells are typically in the tens of thousands of feet, but people have reported depths in feet, in meters, in millimeters. So being able to handle that, along with the more domain-specific, like gamma rays. Null value handling. In the oil field is a very special place. They decided that null value was minus 999.25. Some people do that. Other people call it minus 999. Some people just have it blank. Some people write null. So being able to handle that is important. The rig operation enrichment. This is, again, trying to figure out if your bit's on bottom. Which direction are you actually going? Figuring out if the pumps are actually pumping, or if they're just testing the pistons, things like that. Rig state detection is saying this rig is drilling, this rig is tripping, this rig is circulating, doing a bottoms up. You have to infer all of that based off of trends. Without that information, it's impossible to do further on analytics. Invisible lost time analysis. So that's a situation where there's not necessarily something that broke on the rig, but you notice there's inconsistencies. So you've got rig A that's actually making a connection, so putting two pieces of pipe together. That generally takes 4 minutes on rig A. But on rig B, it's taking 22 minutes. When a rig costs $500,000 a day to operate, that's a lot of money. And then anomaly detection. When you're looking at anomaly detection, this could be as simple as just basic pattern matching, understanding different elements that make up potentially an area where, am I missing data? Is this pump about to fail? Is this sensor not calibrated? You could go as simple as just pattern matching or as complex as, for example, an LSTM. So for our non-functional requirements, we need heterogeneous data ingest, a robust data pipeline, extensible feature engineering, scalable, and reliable. Now, what we mean by this is flexible data ingest, pulling data from those various data sources that I alluded to earlier, robust data pipeline, easy to debug, and trusted. Now, the reason why I say easy to debug and trusted is because there is not a drilling pipeline that exists today that is either of those things. Being able to support existing computational frameworks and runtimes scales up and scales down. There are situations where we're combining 50 billion points. There are situations where we're combining 10. We need to be able to scale up and scale down. Rigs, on average, in the Permian, drill a well every 14 days. So it's variable as to the amount of data that you're actually getting. And then if a data processing workflow fails at a step, it does not continue with erroneous data. This is actually a big one. A lot of the pipelines that exist today that are mostly homegrown, that's kind of how they work. So how is this approach, how did we approach this originally? Now, this came from a situation, we're traditionally a big data shop with traditional big data technologies. What we had done was we had implemented NiFi. Now, if you were in the presentation that was here right before this one, StreamSets, that's almost exactly the same thing. It's an Apache project that is a data flow management tool. So it can pull data from various databases, WITSML servers. It can pull it from a bunch of different places. Its unit of work is called a processor. That's what it uses to collect data and transform and place data. So we utilize NiFi to essentially pull all this data from all these different places, create Avro files, and drop them into HDFS. From there, we used Hive, created external tables from those Avro files, and then used Spark to actually do the computation. Now, the largest issue that we had was we had a BI tool connected, Tableau via ODBC. It was slow. We had to, at design time, create the reports that we actually wanted to show. And the reason is because essentially what we had to do is we had a Spark application that would create the tables that would allow us to report on. And that was to get the kind of the performance that we wanted through LLAP. In order to actually interactively work with the data, we had a Hive interpreter used via Zeppelin to actually be able to interactively query the data. The problem with this is, there were actually several problems with this. Very slow BI. It was very tough to debug the cleansing. Essentially, what ended up having to happen was we would read some data, go through a Spark application, write it back again. Another Spark application would pick it up, read through the data, do whatever it had to do, put it back, and so on and so forth. The I/O got to be a little intensive. The actual data loading process, so this bit right here, can't really see it, but this bit right here. Because of the way that a lot of these more, and I'm more talking about the homegrown databases that tend to be more esoteric versions of databases, it was a little painful to load that data into HDFS. We ended up having to drop entire, or add new files, reload them into Hive via external tables. Chaining the jobs together was also a challenge. Mostly the biggest success we had on that was just creating Jupyter notebooks and just having workflows built in Jupyter notebooks via Python. And it worked to a certain degree, but that just meant we added complexity to our solution. And in order to achieve this, again, all of the functions were re-implemented in Spark. So rig state detection, rig operation detection, parsers, loaders, all of that was rewritten in Spark, or in Scala and put into Spark. So what did we actually achieve? We didn't do very well here. We achieved heterogeneous data ingestion. All the rest of it, it was very difficult to use. So without trying to change a whole lot, what we took a look at was using Ignite with the Hadoop acceleration. This worked okay-ish. I say that because it did give us a boost in our performance. However, it made it increasingly hard to debug the application. And the reason is it still didn't solve all the problems. We still were left with a lot of the same problems. We complexified an already complex problem. And the way that we did that is now when Spark was throwing errors, it was next to impossible to figure out if they were coming from Ignite, to figure out if they were coming from HDFS, to figure out if they were coming from Hive. Because what we did is we aggregated all these logs into Kibana, we sorted on them, and it was impossible to figure out where your stuff was dying. It was, I cannot emphasize that enough. It was impossible. So the very fortunate thing that happened while we were investigating this solution was that Ignite persistence came out. So the ability to actually store data from the Ignite cache and persist it out of memory. So that led to Approach V2. This is more what Approach V2 looked like, and we ended up developing a lot of stuff that sits on top of it, but it allows us to have a lot more flexibility. We completely removed HDFS and Hive. What we were left with was Ignite and a persistent storage. It says configurable. What we used was Cassandra. And the reason we used Cassandra was there wasn't a huge need at this layer for consistency. We did have to, in order to maintain kind of the transactional safety and things like that, we did have to have batch storage that made sure that everything was correct down here. But for the most part, Cassandra served the purpose, or serves, I should say, the purpose of just persisting the data beyond the lifespan of the Spark application. So what does this allow us to do? It allows for very interactive workflows, and we're going to go through what a workflow is in a little bit. We can schedule workflows, and each workflow is made up of functions, which are really just microservices. They're not really micro depending on what framework we're using. But we could use Spark, Docker, Flink, all in one pipeline. And the way that we do that is we essentially kick off each job from the service grid. They're all Ignite services. They're kicked off. For example, I have a Spark application. I'm going to kick that off. It's actually going to start a job in Spark via Livy. That's going to carry it through. It's going to persist the data. Then I could have another job that is kicked off via Docker, via, again, another service grid. And I'll talk a little bit about why we chose to do it via service grid in a little bit. So each instance of a workflow contains its own cache. And I'm going to talk about why that's important in a second. But basically, every step in the workflow has its own cache. There was another reason why we did that as well, and that was tenancy. So unlike, for example, using an RDBMS, which, depending how vertically exotic you wanted your hardware to be, could have solved this problem. We used Ignite. The problem with Ignite, I would say, is it's starting to go in that direction, but the security is still an afterthought for Ignite. So understanding authorization, things like that, to be honest, we just separated out through different caches. We use Zeppelin via the Ignite interpreter. And then workflows are actually responsible for loading the data and processing the data. We actually do still use NiFi. And depending on our real-time workflows, we can also use, we've got an IoT accelerator, which basically puts data onto Kafka, and we could use that as well. And I'll talk about that in a little bit. So, this is basically what it looks like at a very high level. The source is where the location of the data is coming from, and we'll talk about the different places that could be. Essentially, we've got a function that's kicked off by a service in the service grid. That data is then stored in the first cache. We can, if that is a Spark function, it's stored as a data frame. If that is anything else, it is stored using the Ignite API and can be accessed via SQL. And it just chains across into a workflow. The data can be queried, again, by the API or another function. So, again, the function runs as a service from the service grid. And the function receives input from any source. Kafka, JDBC, and Ignite cache. The reason Kafka has a little asterisk on it right now is because we're still working with the Ignite Kafka sync and hope to have that completely done. But for right now, it's JDBC or other Ignite caches. So you can chain workflows together as well, and I'm going to talk about why that's important in just a second. So once the function is applied, you store the result into a new Ignite cache. And the reason is we want to maintain the lineage, and we want to maintain the mid-steps because of branch workflows that we can break off of this. So what are the capabilities of a workflow? We can start, stop, or restart a workflow. Restarting involves removing caches. Stopping just stops it wherever it is. We can execute single functions within a workflow, and you're going to see why that's important in a second. And also pausing execution, and I'll show why that's important as well. It's important to note here, actually, there's a little, due to coloring, you can't see it, but this carries along the data, but also information to the next function about cache information, about where it's supposed to get the information for the next step. So let's take a look at Spark-based functions. So basically, after each function has completed its computation, the data frame is just stored via distributed storage. Now, it really depends on what kind of Spark computation you're doing. So we have computations that range from very small, you could say simple computations that just, for example, do interpolation or a pivot. However, we have much larger computations that take into account spatial locality and the Earth model below, which actually requires a huge cluster. And I'm going to talk about it in a little bit, but that's where affinity data locality starts to really matter. And what we had to take into account was making sure that when we execute the Spark workers, that the data itself is co-located on that node. And the reason is we needed to really design it well to make sure that that co-location doesn't duplicate data more than it has to. So to explain that a little bit more, there are cases in which we will actually create two caches for example, dimension data. So if we didn't want the data to go and traverse the network in order to make a join between several billion points, then what would end up happening is we would create two dimension tables on each, one on each node, so that we didn't end up having that network traversal. So it's actually fairly simple to just write the data frame, and then the workflow would define the table name that's actually done so that the next function in the workflow could pick it up. So one of the big issues was debuggability of the workflow. So this is where the intermediate querying came in. The ability to actually query the data at a mid-step. So you'll remember I said you could pause a function, you could stop you could pause a workflow, you could stop a workflow. This allows you to then investigate the data that's at that mid-step. So let's say that I did a null value correction and I wanted to make sure that my null values were actually corrected. Great. I did a linear interpolation, I did a quadratic interpolation. I want to see that that data is actually correct. Great. Or let's say I wanted to just connect my BI tool directly up to that to show it. That's fine too. Because you get that full SQL 99 capability directly from the data you put in, that's great. You need to make sure that you're using the binary encoding on your data frame to do that, or else you're going to get errors when you try to query it. All right. So applying this to the use case, what this ended up looking like, and what I'm doing is I'm taking a snapshot of the entire workflow I did that I'm going to show at the end, which is the benchmarking one. So I've got a Java WitsML client, and that actually runs in a container. It writes the data via the Ignite API to this. Another channel mapping unit conversion Docker instance pulls that data as well. These are actually running as separate parallel workflows. So we had 6 of these running at the same time, 6 of these running at the same time, but putting in data into different caches. And then for the last one, we had a Spark. In this case, there's actually more that comes after this. We have rig state detection, enrichment, and pivoting. So the pivot is just due to the fact that this data generally comes in a columnar fashion. And what ends up happening is most of the Oilfield tools require that that data is tabular. So we end up having to pivot it and create a whole lot of null values because the data is generally not time aligned. So this is all orchestrated via the workflow API and the scheduler API. And the way that this works is this is using Spring Boot, Akka, and Quartz scheduling to do this. So it's a Spring Boot application layer that sits on top of this. And then we have basically Akka actors that go in that are responsible for making sure each one of these runs and that they are completed. Excuse me. And the scheduler API is there to make sure that these things are running correctly on the correct nodes with the correct data. So here we managed to achieve all of the requirements we set forth. We had heterogeneous data ingest. We had the flexible ingest. Again, we used a combination of Spark for this. We also used NiFi and our IoT platform to do a lot of this. Our IoT platform actually just puts the data into Cassandra, and we're able to put Ignite directly on top of that and read from those tables directly. That was a fairly easy win for us just due to the fact that we didn't have to worry about data modeling beyond that. It was easy to debug and modify just based on the fact that functions are now essentially the workflow is described using a JSON document or XML, either one. And that workflow is just detailed out. I'm going to talk about what we're going to do in the future with that. But it's essentially, I want to do this function, and as long as you point where the jars are, you're able to execute those according to the workflow. You do have extensible feature engineering. If you have a new Java application that you want to throw out there, Scala application, if you have really anything that you can think of, you can put it in your pipeline and just have it executed as part of it, as part of the workflow. It does scale up and it does scale down. Due to the fact that you can add nodes to Ignite and remove them from Ignite, you have a large ability to handle scaling up and scaling down depending on your load. So we've tested this on single node instances and processing 1 well's worth of information up to about 16 nodes. Works and it's fine. The same instance will scale up and down. One thing I will note on this is we did not go for disaster recovery or high availability. That's something that was just out of scope for this project. So in this case, we were just aiming to have something that didn't really have any SLAs associated with it. So to talk about how we actually benchmarked this thing. So we had already had the dimensions tables loaded. So the dimensions tables were just basically mostly from those original planned data stores, the well views and such. So we had 8 functions, which was 6 wells of data, and we had 5.7 billion points. The way that we handled this was, and all of this data was WITSML data, and it came from a WITSML server. We ingested and parsed this WITSML data, and again, that was a Docker function. We had a null value handling solution that was also Docker. We had interpolation, that was Spark. Depth adjustment. Depth adjustment is a situation where those multiple vendors that I showed at the very beginning, the MWD, the Cementer, and those guys are not always using the same reference. So your index is not always right. So we have an algorithm that allows us to shift based off of other pattern markers we find in the data, and that's done via Spark. The drill state detection is done in Spark. Rig state detection is done in Spark. Anomaly detection, for the fun of it, is done in Flink. And we pivot the data set in Spark. A lot of that heterogeneity came from the fact that we just wanted to test how it would work, putting all those different frameworks in. So in V1, everything was implemented as a Spark application. For V2, the computations remained close to their original implementation. So whether it was Java, Scala, C++. In our case, everything was Scala or Java. So what we saw in V1, which was HDFS, was 9 hours. And then without the WITSML download, was 7 hours. So to explain that a little bit, the WITSML download portion of it is taken out because that's more a factor of the server itself. WITSML servers are notoriously slow, and they limit the amount of data that can come out of it at any given time. So it took about 2 hours to download all that data from our WITSML server. Now, when we executed V2, it was 2 hours, and it was actually 22 minutes when it came down to actually doing the processing of it. And a large part of it was we were able to load all of that data into memory. We never had to hydrate that out of Cassandra or anything. Our cluster was big enough that we were able to hydrate out that we were able to hold that data in memory, and we didn't have to worry about hydrating it. So we saw about a 19x improvement over our HDFS Hive solution. So we did learn some things. Apache Ignite is great to speed up data processing without a wholesale replacement of technology. And what I mean by that is we were able to replace it without rewriting the computations that we had done. Unfortunately, we'd already rewritten them to work for V1, but it was nice to not have to do it for V2. And it's nice if we go in to implement this anywhere else that we don't have to worry about implementation or re-implementing stuff in a specific framework. One thing I will say is that Ignite does have a learning curve associated with it. So if you're implementing this into an environment where people don't necessarily understand, a lot of times, one thing I've noticed is that for people who haven't dealt or who don't have an in-memory strategy, things like that, they tend to think of Ignite as memcached or ehcache, something a little thinner than what it actually is. It is an in-memory database. And what ends up happening is that you get misconceptions of ease of use and management. And it is something that you're going to want to do an analysis of if you can onboard that from an operational perspective. One thing I definitely want to point out, accelerating Hive via Ignite was not straightforward. I would say that we have very good Hadoop experts in our team. We have very good Hive people, very good HDFS people. The problem that we had was that it's very difficult to tell who's having the problem. And even with a lot of experience in both technologies, it is very, very challenging to figure out. Big thing, spatial querying. Spatial querying is available via Ignite. And it is available via the open source version of Ignite. The important thing is it's not part of the Apache download. And the reason is because it's LGPL licensed. So you have to download it separately. That is something to take into account if you are implementing this for a product and you're worried about licensing. So I will say that the spatial querying and the performance of actually generating the geopoints and things like that is very efficient. We found it to be quite useful to generate maps, select around a polygon, and say, give me X information about these wells. Understanding data locality in Ignite is crucial for larger data sets. This is a little bit what I was talking about before. Especially if you're joining a lot of dimension tables with a very large facts table, you might end up creating 2 caches on each node so that you have so that you don't end up having all that network traversal where you get kind of this exponential increase in latency. Ignite does work very well inside of Kubernetes. The thing I like about it is we don't have to worry about something like Zookeeper to worry about leader election on top of the stuff that Zookeeper already does. As long as your networking is set up well, we've learned that Flannel and Weave are kind of the 2 networking solutions that we've used in Kubernetes that seem to work really well with Ignite. To be honest, that's our go-to solution now. So for example, OpenShift from Red Hat, that's a very easy way to just kind of get it in there and start operating. And then the thin client JDBC driver, this is a big thing that we found out towards the end of our testing. It does not have affinity awareness of all the nodes you have. So if you lose a node and it's connected to something, it does not switch over. The reason I mention this is because it's very difficult to figure out in the documentation. In multi-node configurations, you're definitely going to want to prefer the thick JDBC client over the thin JDBC client. That caused a lot of hair loss. All right, what's next? So the workflow, the scheduler, all of the application server that I referred to earlier, we're open sourcing that in probably Q1, Q2 of next year. We are going to implement a UI on top of it. So we've been highly influenced by NiFi, StreamSets, those guys where you have a drag and drop canvas and you can basically graphically link together your workflows. So we are working on building that workflow JSON/XML document such that you can now just kind of drag and drop and manipulate your workflow in a designer and then execute it and control it from that designer. Additionally, the implementation of a standard set of functions that can be leveraged on top of the memory grid and then executed via service grid. So things are going to be like join table, split table, null value handling, various forms of interpolation. We are also going to handle very basic things like linear regressions, anomaly detections via LSTM, some of the stuff that I've referred to a little bit earlier. Additionally, we are going to be looking at the implementation of streaming sources via Kafka, the Kafka Ignite sync. So one thing I will mention on this, I alluded to our IoT accelerator that we have that pulls in WITSML data, it pulls in MQTT data, and it streams it in via MQTT. It also outputs via MQTT. The MQTT Ignite sync works pretty well, and for whatever reason I left it off the lessons learned slide. It works pretty well. The largest issue I've seen is that it can get cumbersome when you are subscribed to a large number of topics. It essentially uses the PAHO client to make that connection to a topic. And if you have a large number of topics, let's say that you're using, there's a specification called Spark-Plug-B, which is gaining traction in the manufacturing and industrial process control world. It defines a topic for each node. What ends up happening is you end up overloading that sync and you get very, very strange errors. So that's one thing to think about. So one thing I'll leave you with, I'm at questions now, but one thing I will leave you with is that I did a use case exploration via drilling. But this is very, very, I mean, it translates into heavy industries, manufacturing. It's very similar. You just replace WITSML with OPC. Modbus, it's very, very similar to a lot of other IoT-based solutions. The reason why we went down the road of developing this is because we couldn't find a solution that allowed for legacy, let's say legacy IoT deployments, which is just about all industrial IoT, to easily clean their data, to easily generate insights from their data in such a way that they could reuse a lot of the engineering effort that they had put into it to begin with. So with that, I will stop for any questions you guys have. I know it's the end of the day, so if you don't have any questions, it's okay. All right, yes, sir. Good question. So the question was the workflow predefined, or could I kind of change it? Could I do 3? Could I do 5? It was defined via JSON, but we can stop it and re-upload a new JSON. We can even branch it out. So let's say that we did the first 3, and then we wanted to take a completely different branch. We would just pass it with a separate source Ignite cache, and then run the workflow directly off of that. And it's changeable, basically. I wouldn't say at runtime, but if you stop the workflow and re-upload an XML or JSON, then it'll do it. Yes, sorry, yes, sir.
When you integrate Spark with Ignite, are you able to use Ignite like reference implementation as keys, or you have to do some specific stuff?
So the reference implementation, you're talking about the implement. Sorry, I'm supposed to repeat the question. The question was, were we able to use the Ignite reference implementation for Spark and just store the data frame in the Ignite cache using the Ignite data frame, or did we have to do something else? So are you referring to the documentation?
Kind of like did you have to do anything specific, or
Yeah. So we had to do one thing specific, and the reason is in the Ignite implementation, it's great if you want to go from Spark into another Spark application into another Spark, because it kind of stores it in a way that Spark wants to read the data frame back. But let's say that I wanted to do Spark and then query that with SQL, not in Spark, then what ended up happening was I was getting an exception. I had to pass a parameter in to use binary serialization, then it worked just fine. But it was like a one-line change. Okay, so V1 to V2 resource changes. Very good question. We have very excellent resources, so we kept the same resources. They just learned very quickly. That's actually why I put that second lesson learned, which is it does have a learning curve. So it is very different. If you're a traditional kind of HDFS Hive shop, it is a big kind of change. But if you're used to key value stores, if you've had experience with Cassandra, if you're used to those types of things, it's actually not so bad. It's pretty okay. In terms of, and we had a high memory cluster to begin with, so we didn't really have to make a lot of changes. If, let's say that you had, let's say a cluster that favored maybe more compute, a lot of times you have kind of the Hadoop clusters that favor more dry I/O and CPU rather than memory, then you will probably, it depends on your data set size really, and it depends on whether or not you can wait to rehydrate that data or not. And sorry, the question, to repeat the question, was could we use the existing cluster, or did we have to modify it? Yes? Correct. Good question. So the question was, how are we orchestrating? So for example, how did this guy know, or how did this workflow know when this guy was done to kind of kick off this next one? And that happens as part of a watcher service that we have going on outside of it. So all of these are actually running. So Spark runs in Kubernetes as Spark. The Docker containers run in Kubernetes as either replica sets or actually generally replica sets. The way that they know when they're done is the watcher service that sits there. It's actually inside of the workflow API that watches when each one of these workers are done. So that's how that works. And it uses the Kubernetes API to just kind of spin up pods as it needs to. Yes?
So you run your application on a web by web basis. What I mean is, you load the data of the wells, and then run for 14 days of drilling life cycle, and then for next one start over.
So that's a good question. So in this case, did we take the 6 wells and did we load all of it and then start over? Now the reason why I mentioned at the very beginning that we don't want to get rid of these unless it's deterministically we want to get rid of it, like somebody actually goes in and deletes it. And the reason is because when I referred to that 2-hour time to download this WITSML data, we would rather execute this 6 times and then never have to execute it again, knowing that we've got well 1 cache, well 2 cache, well 3 cache, well 4 cache, and then we can run separate workflows directly off that cache. Now, if we wanted to, if we had something that was looking at all 6 of those, for example, we could source it from all 6 Ignite caches if we wanted to. But those caches don't leave, if I understood your questions correctly. These things are resident so that you can branch off of them and create separate workflows. Yes?
So what was the size of data on the Ignite cluster? Because the virtual state is keeping the data, so that's duplicating the data.
Oh, it's duplicating like crazy. Yes. The one thing I will say is drilling is not your traditional big data problem. I would call it medium to annoyingly small. It's not telco, it's not social media, it's not any of these types of kind of traditional big data use cases. When we set out to do this, if you store the data intelligently, which for us generally means columnar, because what ends up happening is in a tabular format, drilling data actually turns out to be a Yale sparse matrix, so we end up storing it columnar fashioned. If you do that with the right compression, to be honest, it's actually not that huge. So in the case where we had the 5.7 billion points, each well was about a gigabyte source. And then if you just copied that over, for this entire workflow, we were looking at about, I think the total size of that was about 17 gigabytes once we were all done. Because each time we were going through this, like the rig state detection was only adding a little bit of data, and we didn't actually store all of the data again. What we did is we just stored the new features that we created alongside of it, and we could merge those two together via a join table function at the end if we needed to. So. So planning of the co-location, that's a special endeavor, and I'm going to say it works, to use a quote, 50% of the time, it works 100% of the time. So the situation that we have right now is that when we actually go in to plan the data locality versus the Spark application, what we do is we have some metadata associated with the Spark application to understand cache affinity and cache keys, to understand kind of what is required for this Spark function, what is required for this Flink function. We don't have, I don't know that you'd ever implement these distributed computations using Docker, because Spark is Spark and Flink is Flink, and you'd rather use those. In those cases, what we do is we end up distributing it. What we are looking at doing is trying to more natively use Spark and its locality ability and Ignite. That's one thing I've noticed about Spark and Ignite. The locality kind of breaks, unlike when you have Spark and let's say just HDFS, right? So yeah, that's still something that takes a lot of design time forethought to get right. Yes?
If you do V3, what would you change from V3?
Good question. All right. If I did, let me get back to, all right, so here's V2. If I did V3, what would I do differently? To be honest, one of the things I would do is that refactor the data locality thing. I feel like there's a better way to do it, utilizing a lot of the features that Spark has in it and that Flink has in it in order to do the distributed compute. Right now, I don't think that we are fully utilizing those distributed compute frameworks for their data locality as we could be. And that could be a little bit of our learning curve on Ignite not being able to get it. But that's one thing that I think we would do. Outside of that, we're pretty happy with the way that this sits right now. Yeah. Yes?
Can this approach be adapted for other applications such as seismic processing?
Yes, so it could. The one thing I would say about seismic processing though, so if you're talking about going from pre-stack to post-stack seismic, that's typically something, I think that the memory grid would help you. I don't know how much the functions would help you because when you're going from pre-stack to post-stack, that is truly an HPC use case. I don't know. Ignite, I think, could definitely help you. I don't know how much the workflow would help you because when you're going from pre-stack to post-stack, there are a couple of parameters you're going to change, but the workflow itself is relatively static, if that makes sense. You could do it. It just might be overhead for what you're trying to do. All right. Thank you very much.